Alright, so in this video, we're going to talk about sorting. Because earlier this week, I was looking at the Rust cookbook. And I was going through the sorting. I was like, okay, this is cool. Just sorted integers. Okay, this is cool. Sort floats. Something's a little different. And then we got the structs. I noticed that we derived 4 different traits. I was like, wait, what? So we're going to look into that today. Let's get it. Alright, so here is the Rust cookbook thing I was talking about. Table of contents, sorting a vector. We come through here, right? And we see main, creating a vector of integers, cool. Sort. That seems relatively straightforward and simple. And then you would just check it. Alright, then we get to floats. And they're like, okay, you're going to have to use sort by and partial order partial compare. Not exactly sure what that means, but it's just one thing that's slightly different. Meh. So we have the vector of floats. We do sort by, we pass an enclosure, A and B, and we say A, partial compare against B, and then we unwrap it. I'm not going to ask too many questions there. And then we get down to sort a vector of structs. Okay, we have our struct, name and age. And then up here we have derive, debug, understand that, I need to be able to print something out, cool, no issues there. We have equal, order, partial equal, and partial order. And I'm thinking to myself, that's a lot of things to derive. I don't know what those things do. And they even tell us here that we need it. In order to make person sortable, you need 4 traits. And they go down the ones I just named. These traits can be simply derived. You can also provide a custom comparator function using sort by method and sort only by age. Okay, so that bugged me. And then I started looking it up. So the documentation for that comes in the module standard library compare. And they have some stuff here. It's pretty straightforward. So you have the equal and partial equal, just to note, overwrite these operators, whether something's equal or not equal. And then the order and partial order operators overload the comparison operators. But when you scroll down to the traits, here's what they tell you. The equal trait is a trait for equality comparisons, which are equivalence relations. Okay, you want to take me back to college? Understood. Then you have order, trait for types that form a total order. Okay. Then you have partial equal, trait for equality comparison, which are partial equivalence relations. Okay, I guess you're part of this. And then you have partial order, which is trait for values that can be compared for a sort order. So let's break this down. And we're going to go in the order I think is most appropriate. So we're going to start with equal first. So equal. To get the equivalency relation thing out the way, it is just these definitions. Something, a system, or a field that satisfies those 3 properties. Reflexive, which is A is equal to A. Symmetric, if A is equal to B, then B is equal to A. And transitive, if A is equal to B and B is equal to C, this implies that A is equal to C. This is just some random math stuff. Abstract algebra at its best. It's important for what it means, but overall it's not all that important. But let's get to this, the Rust code. So when we look at the declaration for equality, it requires partial equal and it has nothing here. It is empty. And they state that here. This property cannot be checked by the compiler, and therefore equality implies partial equal and has no extra methods. Okay? It seems like it's just a marker. Gotcha. And then derivable. So, I mean, we can use derive as you saw in the cookbook. This trait can be used with derive. When derived, because equality has no extra methods, it is only informing the compiler that this is an equivalence relation rather than a partial equivalence relation. Note that the derive strategy requires all fields are equal, which isn't always desired. So there's two takeaways here. One, they explicitly note that this is just a marker trait to let the compiler know that you have an equivalency relation. Sure. And two, in order for something to be derived as equal, all the fields in that struct, is it just structs or enums? Probably enums as well. Anyway, all the fields have to be equal as well, have to have that property. So in our example over here in this thing, name, strings, they probably implement it, and U32 definitely implements it. So yeah, those are good. We can derive because both of those things have the equal property. Come back to equal. Okay. And then they have the implementation thing here. An example, how can I implement equal? And they give you a book format with enums, just fluff for the most part. That's going to be used here. But the thing to note is, so they implement partial equal for book, and partial equal is the actual one that has the equal function, right here. And that's where it's actually defined. And then equal, as we know, is 0, or empty. Alright, so let's go to partial equal. What do they have here? So they state that partial equal is a partial equivalency relation. What does that mean? Well, that means it has the symmetric property. If A is equal to B, then B is equal to A. And the transitive property. If A is equal to B and B is equal to C, this implies that A is equal to C. However, it's missing the reflexive property, which if you do not recall, that just means A is equal to A. And the reason why it doesn't have that, and they give this example, so that points to them for doing that. We have things like not a number is not equal to not a number, which makes sense. And thus, you do not have a full equivalency relation. Got it. And now let's look at this declaration. So one thing to note here, and because I look at documentation a lot, but I didn't realize this notation, what it meant. This notation here means that there's a default implementation for this method on the trait. Anyway, we have a partial equal, and it's looking at the right hand side and making sure that's equal to self. So you're comparing two things that are the same. The right hand side needs to be size, which means the size of the object needs to be known at compile time. And then we have equal, which is going to return a Boolean, which we already looked at because we saw the equal trait implementation. So we know that's a thing. One thing we didn't see is the not equal, which has a default implementation. And we can look at that real quick. Open that up. We see partial equal, and here's the not equal. And the default implementation is just the opposite of equal, which makes sense. This is why we don't have to implement it. Anyway, going on. So this is derivable as well, as we saw earlier in the example. And it says pretty much the same thing. When derived on structs, two instances are equal if all fields are equal and not equal if any fields are not equal. Then when derived on enums, each variant is equal to itself and not equal to the other variants. Okay, all the fields have to have some sort of equality that they can be measured by, as in if all the fields implement partial equal, then we're good, and then we can just derive it. Pretty straightforward. That's a common theme. So then we go through the example, right? We have enums for the book again, the fluff, and it's formatted differently, which is sort of weird, but meh. We have the book, and then we have the partial equal, same as before, where we only implement equal, and we only have to implement equal because that one doesn't have a default implementation. And then to give us examples down here. All right, so going to order, right? So actually, no, let's do a recap real quick. Equal depends on partial equal. That is noted. So if you have anything that has the equal trait also implements partial equal. It's not always the other way around. You can implement partial equal and not have equal. And the example that they've shown, or at least they implied, was floats, which they did right in the example. They did right here, because you have not a number, and not a number is the float thing. And they also pointed that out in the example over here in the book where they did the partial compare on floats. Because if they could do just a regular compare, they would have. All right, moving on to order. Order talks about total order. What is total order? And they give us a slight definition right here, 2 bullet points. Total and asymmetric. Exactly one of A is less than B, A is equal to B, or A is greater than B is true. And transitivity, as in if A is less than B and B is less than C, this implies that A is less than C. The same must hold for equal and the greater sign. It's more or less these basic properties, which everybody's probably seen in algebra, just regular numbers, integers, and floats, mostly integers, needs to be hold true. So that's pretty straightforward, understood. It just has a weird word that associates those two things. Anyway, let's look at the implementation. So for order, we have it requires equality, so the equal trait, which means it implicitly requires partial equal, and then it requires partial order, which we haven't gone over yet, but hold on, we'll get there. So we see we have a compare, all right, and it returns an ordering. What is an ordering, you say? It's an enum thing that's here, and that just means it's either less, equal to, or greater, the 3 options that we have. Got it. Close that. And then we have default implementations for the other ones. So we want to find the max, the default implementation. We want to find the min, this is default implementation. This clamp thing, I'm not exactly sure what initially I wasn't sure what it was. Then I clicked on it and it went through. It's in nightly, it's not even in stable. But if you want to read it, it's here. It does something sort of weird. It takes in a min max and compares against the number, and then returns one of the 3, depending on which one is closer to the actual number. But that's a story for another day. I'm not ever using that, at least not until it's in stable. Oh, actually, before we move on, to note, we only have to implement compare, which makes sense. Everything else is default implementations. And then we get the similar story when it comes to derivable. When derived on structs, it will produce a lexicographic ordering based on the top to bottom declaration order of the struct's members. Oh, okay. When derived on enums, variants are ordered by the top to down declaration order. So going back to this first sentence, a lexicographic ordering means top to bottom, right? So that means in this example, we're ordering by name and then by age. And then in this main, which we haven't really looked at yet, they have the people, they're creating their people, and they're calling sort on it, and they're making sure they're sorted appropriately. However, if we change the name and age, the ordering of this all breaks. So this seems kind of fragile to me. No, I won't use sort directly on structs because that doesn't seem appropriate. And it also implies to me that anytime you rely on sorting in your code, you should definitely test it, because if it's this kind of fragile, you don't want that kind of bug. Especially if somebody else goes in and just changes things willy-nilly, or you forget and you change things. Anyway, moving onward. Okay, that is good to know. How do I implement order? You must implement the compare. And you must have implementation for partial equal, partial order, and order must agree. So this is a good point that they have. And they have this on a number of this one I think on also partial order, which is some of these definitions have the possibility to disagree with each other, because let's say you derive partial order and order, right? Those two have definitions that have equivalency in them, so you can compare things that are equal, but you also have traits for equal and partial equal. So if you wrote those out explicitly yourself, then you have the possibility of entering a realm where your equal does not equal their equal, and thus your struct has conflicting information in terms of what is equal and what is not equal. And they note that. They say it is easy to accidentally make them disagree by deriving some of the traits and manually implementing others. So the warning is here. Anyway, let's look at the example. How to implement order. We see here that we have ordering, so we're importing that. And just glancing down, we see that we use it here and here, so that's needed. We have a struct for person. We derive equal. We do not derive partial equal, but if we look down here, we implement it ourselves, and we implement the only function that is needed, which is equal. Okay. Our person struct has ID, name, and height. 3 fields. These 3 fields all can be derived for equal because none of these are partially equal. They all have the equivalency relation reflexive property. Alright, so implementing order for person, we implement the compare, which is the only one we need to implement, and we're ordering by height, and we're doing height.compare. So one thing to note here is that it seems as though it is common to just look at the field explicitly, the one you want to compare by, and if it is a primitive or it implements order itself, then you just call order on it, or the compare, which is from its order trait. And that's how you go about doing it. And that's going to return a ordering enum, which is less equal to or greater. And then partial order, which order depends on, which we haven't looked at yet, but here's a glimpse of it. It has one function or one method, and it's partial compare, and it returns an option. Option meaning that it may be none, which I guess makes sense because if you're comparing not a number and not a number, you can't say it's less than, you can't say it's equal to, and you can't say it's greater than. So you're going to have to say, shrug your shoulders and return a none. Okay, that makes sense. And then partial equal, which we already kind of looked at. Just the equal method, and we're doing this on height. So just looking at the explicit thing that we want to look at. And given that height is a primitive, we can just compare it outright. And it returns a Boolean. So yeah, that's all we need to do. So cool. Let's look at partial order. So partial order doesn't have any highlighted big words here, but it does tell you here a comparison must satisfy for all A, B, and C. And this looks like this is where the heavy work is being done. It has to be asymmetric and it has to be transitive, which we already look at transitivity. That's the A is less than B, B is less than C implies that A is less than C, holds for all the other operators. Okay. And it has to be asymmetric. So if A is less than B, then the opposite, or A is greater than B, as well as A is greater than B implies that not A is less than B. It more or less means that you can add negatives to your statement and just can go back and forth. But okay, cool. Looking at the Rust code, we see that this is actually where all the work is being done. So partial order does the right hand side thing. It needs to be compared against something that is equivalent to itself, so the same object type struct, and it requires partial equal. Okay, and partial equal also has a right hand side thing. It needs to be sized, but so does partial equal, so that makes sense. And we see this is the only method that we have to implement, partial compare, and we noted that on the previous one we were looking at order. And returns an option, ordering. We know what those two things are. Cool. And then we see we have default implementations for less than, and less than and equal to, greater than and equal to. And I actually haven't looked at these, so let's take a gander because I'm curious about the less than and equal to, and the greater than and equal to. So we do less than and equal to here, and we have matches, partial compare, and it looks like this is the quote-unquote arm. I haven't used this macro before, but that's what it's seemingly doing, just creating a match for us. And it looks like if less than is true, or if some equal is true. So it's just doing if this or this is true, then okay, cool, that makes sense. I was just curious how they did that since the ordering only has the less than, greater than, or equal to. Anyway, moving onward. So default implementation for all of these. Got it. The derivable has pretty much the same story. It will produce a lexicographic ordering based on top to bottom declaration order of the struct's members. When derived on enums, variants are ordered by their top to bottom declaration order. Okay, yeah, same story. So how do you go about implementing this? And it's a partial compare. And the reason why it's a partial compare is sometimes things aren't true. The same thing, they don't have the reflexive property as we covered earlier. So implementations, oh, here we go. Partial order requires your type be partial equal. Yes. Implementations of partial equal, partial order, and order must agree with each other. It is easy to accidentally make them disagree by deriving some of the traits and manually implementing others. This is just that big warning sign again. If you're going to implement one, you should probably implement all of them just to be consistent. If your type is order, you can implement partial order by using compare. So in this example, this is where they do that. Let's start from the top, right? We have ordering, which we know it's here. This example is almost the same as the other one. Actually, might be exactly the same. We have ordering, which we need for the return types. We have a person struct. We derive equal. The person struct still has the same fields. And in the partial order, they use self.compare. And the reason they can use self.compare is because they know this thing already has order defined. And if you have order defined, if you adhere to the order trait, then you can just directly use compare. Which I think is a little circular, but at the same time, it does make sense. So if this didn't exist, this would give you a compilation error. Moving onward. So if you don't have order and you just want to implement partial order, here's an example of that. We have ordering, we have a person struct. We know there is no equal here, no derived equal. All we have are our partial equal and our partial order. So the bare minimum needed for partial ordering. And here we're only ordering by height. So it's just explicitly on height. All right, so when I was looking at these examples, I noted that I either derive it and order on everything in the lexicographic order, which seems haphazard and kind of scary, or I can sort and order and do all that stuff based on a single field. That's the impression you get when you look at this. But if you go back to the ordering enum page, everything changes. So the compare function returns ordering enum, right? But then you got to look at the methods on the ordering enum. So if you want to reverse things, they have a reverse. But going back to the multiple thing, right? They have a then. So you can order on multiple fields if you wanted to. You just have to do that then thing. So here's their example of that. They have a let x equal this tuple, let y equal this tuple, and then you're doing the comparison on the first one, then the second one, then the third one. So yeah, knowing this and knowing that you can just manipulate off of order, like chain things together so you can do multiple orderings, is how you would go about sorting by multiple fields at once, which I thought was very good information to have. And there's some other cool stuff in here as well. Mostly, this is the coolest part. But yeah, so going back to this example, Rust cookbook, right? Let's copy this code and put it in our editor and then break it and then fix it. So let me make this a little bit smaller so I could get all of it. Oh wait, there's a copy button on the side. Copy to clipboard. Let me open my editor. Alright, so I open my editor. Get rid of these windows. And I'm going to copy and paste the code. Paste it. We have it here. Do a quick walkthrough. Derive, debug, equal order, partial order, which we understand what those are now. I'm good. Those are not going to make me angry. We have person struct, string, age. We have a associative function on it, creating new people. We create the people, Zoe, Al, John, with the different ages, and then we sort them, and then we assert that the ordering is appropriate. And then we do a compare by age. So they do a sort by age. Okay. And then yada yada yada. Cool. So to make sure this works, let's run it. Cargo run. Probably move this over a little bit. And it doesn't print anything out the screen. We just know that it worked because it didn't fail on the asserts. Understood. So we change this just to illustrate the lexicographic ordering issue thing. Let's just rearrange those two things. Bam. The left side and the right side are no longer the same. So yes, we did read about ordering and how we can implement all of those from scratch. But in cases like this, it's best just to use sort by. I could implement all of this from scratch, but I don't really need to sort by. They did the closure thing, right? A, B, and then A dot compare. They did name. No. A dot name. Compare B dot name. Something like that. Isn't that it? Sort by. Oh, wait. Other needs to be B? I don't know what I'm actually doing wrong. Let's see if that runs. And there was an error. Huh? Oh, it's expected to be a string. Yeah, name. Thought that was right. Needs to be a reference. Compiler-driven development. I'm starting to learn what that is. So now everything works as expected. And then I'm pretty sure this returns an ordering. So then we can do, and then compare by age. Then, how did they do in the example? Let's look at that real quick. Ordering. Then, and then you have the comparison thing again. Cool. Then A dot age dot compare B dot age. Do you need to be a reference too? I thought it gets copied automatically. Just a number. Ta-da! Alright, so with that, we reached the end of the video. I think the moral of the story is When in doubt, yes, you could derive these things, but if you're depending on sorting, use sort by just to make sure it's explicit. You don't want things accidentally changing and breaking everything in your code. That doesn't sound like a good day. I thought this was enlightening for me, so I thought I would share it. I hope you all will appreciate this. If you like the video, hit like, subscribe. Outside of that, peace.